we've done it. We now have one of Maxwell's equations in both forms. We have Gauss's law in both the integral form, the integral of E dot dA is Q enclosed over epsilon naught. This is the integral form that perhaps you're used to. And then we also showed, through the use of the divergence theorem, that the integral of del dot E, the divergence of the E field, is equal to rho over epsilon naught, where rho needs to be sort of a continuous charge distribution in space. This is the differential form. And they really are the same thing. And you can kind of see the relationship between them, I think, if you just think about a point charge or just a small charge. We have thought extensively about that. And when you have a point charge like this, with our, we'll go back to field lines for now, our field lines coming out. In these kinds of problems, the kinds we do in freshman physics, it makes sense to use the integral form. And the reason is you can use it with just the charge enclosed. You can have a Gaussian surface, you can do your vector calculus out here, and you can do it with finite charges. This can be a point charge, this can be a sphere of charge, this can be a rod of charge, it doesn't matter. As long as it's enclosed, you can just stick all of Q right there. And you can do your vector calculus sort of separate. The differential form isn't as useful here because you really can't use it for a point charge. Your charge density has to be described by a smooth function. You don't want to get into, well, the charge density is one value in the sphere and then it's 0 outside, and therefore you have to do those boundaries differently for the E field. It's all very confusing. So that's the reason you really work with the integral form more, is because it's more useful in these kinds of situations. The differential form is useful really when you're manipulating fields and thinking about fields, perhaps if rho is 0. It's really telling you how the E field behaves. It behaves in a way that it only diverges when a charge shows up. And that's another thing you can see. We talked about how divergence is like the creation of a field. Well, the E field is created when there's charge. So the field is very divergent right here where there's a charge. The field is not divergent out here. It's just field lines going right through. You can also bring up the question, can you use it at all? Is it good for anything other than manipulating fields? So I want to show you a problem where you can use it. We'll do one problem and do it one way with the integral form, and we'll do it back with the differential form just to show you it is possible. So let's look at just a sphere, a charged sphere with charge density uniform, charge density rho, constant throughout the sphere, and just ask what is E inside. So if you're going to use the integral form, you would draw a Gaussian surface, a spherical Gaussian surface inside, centered on the sphere, all the standard stuff we talked about in the Gauss's law chapter, and you'd say the integral of E dot dA, well, E vector and dA vector are the same direction, so the dot product goes away. E is constant over the surface due to symmetry. It comes out of the integral, and you end up with E times the area of that Gaussian surface, if it's at some radius r, is 4 pi r squared equals the charge enclosed. So if this thing has a uniform charge density rho, then the charge enclosed is rho times the volume of the Gaussian sphere, rho times 4/3 pi r cubed over epsilon naught. And all kinds of stuff cancels. And what you find is that inside a sphere like this, E, well, the magnitude of the E field we're finding is, what is it, rho r over 3 epsilon naught. The E field inside a sphere is 0 right at the center, has to be due to symmetry, and it just increases linearly with radius. The E field gets bigger, pointing out in a radial direction. We figured that out from the symmetry, so we can give it a vector description. So that's what the E field does. Now with the differential form, you could go the other way. You could try to take the divergence of that E field and see if you get the same charge density. So that's one thing you could do with it. So let's do that, see what happens. Well, it's a little complicated. So this is Gauss's law. This is always true. Regardless of what coordinate system you're using, del dot E is rho over epsilon naught. But how you use del dot, how do you write del dot E mathematically does depend on the coordinate system. So in Cartesian coordinates, it was just the partial d dx of the Ex of the function in front of the I hat, and d dy of the part in front of the j hat, d dz in front of the k hat. Well, if you go into cylindrical and spherical coordinates, the unit vectors change direction depending on where you are. That's the evil thing about cylindrical and spherical coordinates. And that makes the vector derivatives, the dot product, or I'm sorry, the divergence and the curl, very complicated. So let me show you then what the spherical divergence looks like. So if we were to have del dot V, and I'm going to go back to V to make it clear I'm not talking about the electric field here. This is just a spherical divergence for any vector field. It's 1 over r squared d dr of r squared times Vr. So that's one term. And remember, the divergence gives you a scalar, so you don't have to worry about I hat, j hat, k hat. This is just the part, Vr is the part that would have gone in front of the r hat if we were to write a vector field Vr. And then it's 1 over r sine theta partial d d theta of sine theta v theta. Like that for one angle, and then there's a third term for third angle plus 1 over r sine theta, and then it's d v phi d phi. Those are the three terms. It kind of looks like in Cartesian you had sort of an x part, there's the x, Vr, you had a y and you had a z. It's just much, much more complicated. Okay? But let's try to apply it. So now let's apply this big nasty thing to del dot E. Well, fortunately, we have very nice symmetry that's going to help us out. Our E field only has the r hat component. We only have ER in this case. Okay? So our E theta is 0. It never points in the theta direction. Our E phi is 0. It never points in the phi direction. So we do have it down already to 1 over r squared d dr of r squared. And then this is rho r over 3 epsilon naught. Rho r over 3 epsilon naught. So there's our divergence. Okay. So this becomes, I'll just sort of running out of board here, so I'll take some shortcuts. This becomes rho r cubed over 3 epsilon naught. And I take the derivative of that, the partial with respect to r, that's 3 rho r squared over 3 epsilon naught. And then times the 1 over r squared. So 1 over r squared times 3 rho r squared over 3 epsilon naught. And now you can see r squareds cancel, the 3's cancel, and you end up with the constant rho over epsilon naught, which of course we know is what del dot E is. That's Gauss's law. So there, that was one problem example where you can kind of go both ways. You go the opposite direction, but you can apply both to the same problem. If you wanted to make it more interesting, you could do, instead of a constant rho, you could do a rho that varies in space. And then you could do this way, and you could get a weird E field and go that way, and you could find a function for rho instead of just finding rho over epsilon naught. So anyway, they are the same law. Integral form, differential form, they tell you the same thing. They're just useful at different times when you're working on problems. Our discussion of divergence theorem gives us yet another law, much easier. Remember Gauss's law for magnetism. There are no magnetic monopoles, there are no sources of magnetism, there are no charges in magnetism, so it's equal to 0. Well, by the exact same math that led us to the E field, you could simply replace the B with an E, essentially, and you would find that del dot B equals 0. So there is a second Gauss's law in both integral and derivative forms, and the way you would apply them, everything is just like the E field. So there is another way we can apply del to a vector field. Before we did del dotted with a vector field, that was the divergence. Now we're going to do del crossed with a vector field, and this is called the curl. So we need to look a little bit carefully about mathematically how do we take the curl. And you think, we know, we've talked a lot about the cross product, that F, for example, is Q V cross B. We talked extensively about what that means. That means the magnitude of V times the magnitude of B times the sine of the angle between them. And then you get the direction by the right-hand rule, right? Well, here we need to go a more sophisticated mathematical definition of the cross product. We need to really do it at the more fundamental sort of vector level. So because we're dealing with something that's not a real vector, we don't have two vectors that we visualize. We have the del operator. So we can also define it like this. If we have del cross with a vector field V, that's equal to the determinant of a matrix where you put I, J, and K first, and then you put the first thing, in this case not a vector but an operator, ddx, ddy, ddz, and then you put the second one. In this case, it's what goes on the I hat, Vx, what goes on the j hat, Vy, k hat, Vk, keeping in mind those can be functions of x, y, and z. Those are not constants, even though I'm writing them like that. So if you really want to get into this, you got to know how to take that determinant. So you say I hat times this, or minus this, and then j hat, this, minus this, and k hat, this, minus this, although there was a minus on the j hat. So it's this pattern. Maybe you've seen it before. I won't belabor it because it's math. But if we really wanted to write this all the way out, we would see that it is, on I hat, it's dvk, or what, kz, dvz dy minus dvy dz. That's the I hat component. And then when you move over one, you always have to go negative. So you'd say minus, give one way to do it, dvz dx and minus dvx dz. And that is j hat. And then plus, now we're doing k hats, or plus, minus, plus, and then dvy dx minus dvx dy. There you go. And eventually you sort of memorize the patterns there. So you can see what's interesting about the cross product is all these partials, it's never, x, y, or z's function with itself. It's always the partials of like the vz component. The vz part of the field must have a y component, or the vx must have a z component. So it's all, the determinant mixes them up like that. So that's how we get it down to individual components if we need to do that. The math is fun, but what does the curl really mean? We kind of had a feeling for divergence. That means the creation of field. What does the curl mean? Let's look at some examples. So the curl, if I had to put it in words, I would say it is how much the field makes something twist. Okay? You'll see what I mean as we draw some fields. Let's start with a uniform field. So let's say that V is 5 I hat plus 0 j hat plus 0 k hat. That's just a uniform field pointing to the right with magnitude 5. Right? So we could draw a field like that. These vectors, say, are 5 units long, and they're all the same size. They're all pointing in the x hat direction. Oh, let's do another layer. Okay, so to decide sort of visually if something has curl, I like to just imagine drop a disk in it like this. Put in a disk, a little solid disk. Of course, we're thinking in 2 dimensions. It's really a 3-dimensional field, but let's just do it and think about it in 2D. And ask yourself, will the disk start to twist? If we think of the field vectors as sort of frictional forces pushing on the sides of the disk, will it feel a net torque? Will it twist? That's what I mean. How much does the field make something twist? Okay. Here you would say this doesn't look like it's going to twist. It has some vectors on this side kind of making it want to go around that way, but it has some vectors on this side kind of making it want to go around that way. And since it's symmetric, they're equal and opposite, and they're just going to cancel out. So here I would say it doesn't appear to have any curl. And mathematically, you're right, it's not going to have any curl, right? Because all those terms in the mathematical, in that determinant, all were partial derivatives. So if you take partials of zeros or fives, you're going to get 0. Okay? So this, the curl del cross V, is definitely 0 in this case. So let's look at one that's not uniform. Let's look at a growing field. So let's see, let's have V equal, let's let it be some x, let's just let it be x on the I hat plus 0, the j hat plus 0, k hat. So instead of 5, it's going to increase. We're going to have short vectors here. Oops. All small vectors where x is small, and then they get bigger as you move to the right, and they get even bigger as you move farther. They're just increasing with x, and they're doing it linear, and I don't know if I'm drawing them perfectly linear, and my voice is getting louder when they get longer. I'm not sure why. That's just for dramatic effect, I guess. So there it is, a growing field to the right, the field x I hat plus 0 plus 0. So let's do our thing. Let's drop in a disk, solid disk, and ask ourselves, is the disk going to feel a net twist? And again, this one is not, because it feels some vectors here pushing this way. The vectors are kind of growing. Maybe they're pushing a little harder here than here to make it want to twist, but the exact same thing's happening over here. So again, when I look at that and say, is that giving me any twist? I would say no, it really isn't. And if you were to go through the, if you were to evaluate the curl of this, mathematically you would also get 0. Because remember, every one of those partial derivatives, it was taking the partial of one of the components, say the x component with respect to z, or the x component with respect to y, or the y component with respect to z. They were always, or x, they were always crossed, right? So if we just have something in the x component that was going to have a partial, but it's with x, that's not in the curl. Okay? So if you go through and do this curl, you'll still get del cross v, it's still 0. And in our little story here, it also appears to be 0. Let's do another one. It would seem to make sense to do one that does have a curl. All right. Let's do a field. I don't know what to call it, but I've given the other two names. So let's do one. It's growing laterally. And what I mean by that is that it's V equals Y I hat plus 0 J hat plus 0 K hat. This is probably the simplest field you can make that has some curl. So let's think, what would that look like? What we're saying is that the field still points in the x direction. Here's some little field vectors here. But as you go up in the y direction, they get bigger, like that. And there's another big one, but then they get smaller when you go down here. Another big one, they get smaller when you go down here. Okay. You could also draw this with field lines. You could have a low density of lines down here, and the density is getting higher and higher up there. So I'm drawing it a little bit awkwardly here with just a little quiver plot. But now, if I drop in my disk, you can see what's going to happen. Drop in my disk like this, and ask ourselves, is that thing going to feel a twist? And now, maybe you can see that it is. We have big vectors here kind of pushing it around like that. We have little vectors here pushing back. So the net effect is it does feel a net twist on this object. And sure enough, if you were to do the cross product, you would actually, or I'm sorry, the determinant to get the curl, you would actually have a value. Because on the term where you take d dy, or when you take dvx dy, here it is, it's 1. And that shows up on the I hat, so it ends up being, or or it shows up second in a list, so it's -1 is the answer in the k-hat direction. Because so curls are vectors, right? So it's a cross product. So in this case, del cross v, the curl of v is -1 in the k-hat direction. So that's telling you even something further, is that the curl of the field is what makes it something you want to twist, and then as we often have in physics, the vector that you use to describe that is perpendicular to the plane of the motion. In this case, it points in on the z-axis. It happens to be in, and there's even a right-hand rule. Look at that. It makes it curve this way. Take our right hand, follow it around. Z has to be this direction in this case because we have x cross y. Z is out of the board. It's negative. It's into the board. Everything makes sense. Okay. So curl is not mean that the field is curvy. Okay. Here, I've given you all three fields. In all three fields, the field was never curvy. It was always just straight lines. It was just simple linear functions or constants. But this one actually had a curl, even though the field always only points to the right. You can still get a curl. You can also get a curvy field that has no curl. So just when you see a field with the vectors kind of making smooth curves, don't assume there's going to be a curl. So let me give you a fourth field, which I have no pre-planned name for. I'm just going to call it the curvy field. But it's fairly simple. It's that V is x I hat plus y j hat plus 0 k hat. I certainly don't want to draw it in 3D. Okay. So let's think about that field for a second. If we were to draw sort of an xy thing going on like that, well, it's always just x, y. So if you go along this line, it just kind of grows. And if you go negative x, negative y, it points down like that. And then if you go on these lines, it points in towards the origin like that. Like that. And it points, I'm going to cheat, look at my notes. Yes, points in when you come here. Like that. That doesn't look curvy, but if you go and add other vectors around it, you actually get that it kind of makes a very curvy looking thing. If you do a quiver plot of it, it kind of does stuff like this. And then they get bigger. Like that. That one goes that way. The top kind of goes like this. You get little vectors making paths like that. And on the right it goes, yeah, the right would go up. Oh yeah, it's going to follow this kind of pattern, so you get a little one like that, and then it gets bigger when you get farther away, of course, like that, and then this one comes around like that. So if you ever want to make this, I've seen some of you making very cool vector plots on MATLAB. It's a very curvy looking field. It's kind of curving around like this, curving around like that, and like that. But mathematically, is 0. And you can see why. We only have x on the Vx function. We only have y on the Vy function. All those partial derivatives are going to be 0. You're not going to get any partial derivatives. So even though this is curvy, it's hard to, really see it exactly. But if you were to drop a little puck in here, you might say, well, the field looks curvy. Surely it's going to spin. But actually, no, it doesn't. The curvy is not the same as a twist. If you look, this one's kind of pushing up and would make it go this way. So it might go that way. But this vector is kind of making it go this way. But maybe you can see these weaker vectors that might make it twist less, they follow the contour better. Right? There's more of these small vectors making it want to push this way. There's less of these big vectors making it want to push that way. And in the end, they'll cancel out if you work it all out mathematically because this field has no curl. It's just curvy. So curvy and curl are not the same thing. Very long explanation of that.